Hello everyone. Section 2.1, Conditional Statements. Example 1, express each statement in if-then form. All equilateral triangles are isosceles. You can see we have a hint here, which is to begin this phrase with if a figure is. So in other words, if a figure is an equilateral triangle, then it is an isosceles triangle. The diagonals of a rectangle are congruent. I'm going to use the hint from part A. If a figure is a rectangle, then the diagonals are congruent. All students love vacations. Again, we have a hint here. Begin with if a person is. So, if a person is a student, then he/she loves vacations. Every rectangle is equiangular. So again, I'm going to go back to the hint up here for parts A and B. If a figure is a rectangle, then it is equiangular. He will drive provided it doesn't snow. If. So, what's the conclusion in this statement? He will drive if, this should say if, it doesn't snow. Or provided it doesn't snow. He will drive provided it doesn't snow. So the conclusion here is he will drive. That's the conclusion, is that he's going to be driving provided it doesn't snow. So, if it doesn't snow, then he will drive. Alright, x is greater than -2 whenever -4x is less than 8. What's the conclusion here? What are we concluding? We're concluding x is less than -2 whenever this is true. So, if -4x is less than 8, then x is greater than -2. Alright, that's example 1. Now move on to example 2. State the hypothesis, the conclusion, and whether the statement is true or false. Okay, I'm going to save a little time. I'm just going to do a single underline underneath the hypothesis and the double underline underneath the conclusion instead of rewriting them all. If it is cloudy, then it will rain. The hypothesis, it is cloudy. Notice I did not underline the word if, because our definition of hypothesis is the part following the if. It doesn't include the word if. So, it is cloudy. Conclusion, it will rain. Again, do not include the word then. Is this true or false? Well, it's a false statement. How do I prove it's a false statement? We do what's called a counterexample. We find a day where it's not raining, but is cloudy. Okay? So a counterexample is true for the hypothesis, but false for the conclusion. So you find a cloudy day that is not raining. So that's true for the hypothesis, false for the conclusion. All right. Part B, hypothesis, conclusion, and true or false. Well, to figure out if it's true or false, let's do a little bit of algebra. 3y plus 7 equals 10. 3y equals 3. Y equals 1. Y equals 1. True. Okay. This is not in our typical if-then statement form. That's fine. The hypothesis is still the part that comes after the if. So x is greater than 3. The conclusion, x is greater than 5. Is this true? No. This is false. How do I prove that this is false? Again, we find a counterexample. I find a number that works in the hypothesis but doesn't work in the conclusion. A number like 4. 4 is greater than 3 but is not greater than 5. There are many of them. 3.5, 4.5, 3.6, 4.7. Any of those numbers are true in the hypothesis and false in the conclusion, which make them all good counterexamples, proving this is false. Okay. Part D. I will win the race if I am a fast runner. Hypothesis, again, the part that comes after the if. I am a fast runner. Conclusion, part that comes after the then. Well, the then is implied in this statement. I will win the race. Is this a true statement or a false statement? This is a false statement for a variety of reasons. 1, just because you're a fast runner doesn't mean you're the fastest runner and you're going to win the race. 2, just because you're a fast runner doesn't even mean that this is a running race. This could be a car race, or a motorcycle race, or a bicycle race, swimming race. And a fast runner is not going to do you a lot of good in those types of races, so it doesn't guarantee you that you're going to win the race. All right. Part E. 2 coplanar lines that do not intersect are parallel. Now again, this is not written in if-then form. Let's figure out what the conclusion is. Okay, the conclusion is going to be they are parallel. Okay, two coplanar lines that do not intersect are parallel. So if 2 coplanar lines do not intersect, then they are parallel. So if I write it in if-then form, hypothesis, conclusion. Is this true or is it false? This is true. In fact, this is a really good possible definition for parallel lines. Okay, part F. We don't need to do the truth value for this one. All members of a soccer team have practice today. So, if someone is a member of the soccer team, then he/she has practice today. Hypothesis, someone is a member of the soccer team. Conclusion, he/she has practice today. Alright, example 3. Write the negation of each statement. The car is white. The car is not white. It is not snowing. It is snowing. Alright, we use negation to write the inverses. Example 4. Let P be you are in New York City. Let Q be you are in the United States. Write each statement in words and decide whether the statement is true or false. So the conditional statement is P implies Q. So this arrow means implies. P implies Q. You are in New York City implies you are in the United States. How do we write that in if-then form, though, as a conditional statement? So, if you are in New York City, then you are in the United States. So is that a true statement? Yeah, if you live in New York City, you live in the United States. True. Okay. Converse. Q implies P. So the definition of the converse statement, which you wrote up above, is that you switch the hypothesis and conclusion of the conditional statement. So, if you are in the United States, then you are in New York City. False. And again, to prove that that's false, you find a counterexample. Find a place in the United States that's not in New York City. If you're in Boston, you're in the United States, but you're not in New York City. There's a counterexample. The inverse. Not P implies not Q. So that's not. This means negation, negation. So the negation of P implies the negation of Q. So if you are not in New York City, then you are not in New York City. And again, this is false. How do we know this is false? Again, we found a counterexample. If I'm not in New York City, so I'm in, oops, this last piece should say U.S. Typo. If I'm not in New York City, I'm in Chicago, then I'm not in the United States. Well, I am in the United States because Chicago's in the United States. So that's a good counterexample proving this statement is false. Contrapositive. Not Q implies not P. The negation of Q implies the negation of P. So contrapositive, we switch the hypothesis and the conclusion, and we negate both. If you are not in the United States, then you are not in New York City. And is this true or false? Well, this is true. It's impossible to find a counterexample. If you're not in the United States, then you are most definitely not in New York City. Okay. What do we notice from this? And this is important because we're talking about equivalent statements. The conditional statement and the converse here do not have the same truth value. They can in other situations, but they don't have to have the same truth value. So just because a conditional statement is true does not mean that the converse must be true. That is not the case. Same thing with inverse. Just because a conditional statement is true doesn't tell you any information about the inverse. But what are equivalent statements? Conditional statement is true. Contrapositive statement must be true. If the conditional statement is false, contrapositive statement must be false. They are logically equivalent. They always have the same truth value. Converse and inverse are logically equivalent. They must have the same truth value. If the converse is true, the inverse is true. If the converse is false, the inverse is false. Okay, example 5. Assume that the given statement is true. Then tell what you can conclude if each statement in A through D is also true. If no conclusion is possible, say so. All right. We're given that a quadrilateral is equiangular, then its diagonals are congruent. So if a quadrilateral is equiangular, then its diagonals are congruent. We're told that ABCD is equiangular. So this is a quadrilateral that has equiangular has equiangular angles. Well, if that's the case, if this is true, which we're told it is, and this statement is true, then this conclusion must be true. And the diagonals of ABCD are congruent. Now, we actually know which segments are the diagonals. AB is a side, BC is a side, CD is a side, and AC is a side. AD is a side. AC and BD have to be the diagonals. AC has to be congruent to BD. Okay, part B. PQRS, quadrilateral, has congruent diagonals. We're being told that this is a quadrilateral and it has congruent diagonals. We're being told that the conclusion is true. Just because a conclusion is true does not make the hypothesis true. That's what we were talking about a second ago with equivalent statements. Just because a conclusion is true does not mean that the hypothesis is true, because the conditional statement and the converse do not have to have the same truth value. They might, but they don't have to. So, for part B, no conclusion is possible. Part C is a little bit trickier. In quadrilateral WXYZ, the measure of angle X is 80 degrees. Now I have a bunch of students who will say, well, if the measure of angle X is 80 degrees and all four of them have to add up to 360, it can't be equiangular. If it is equiangular, then all four of them are 90 degrees. So it is not an equiangular quadrilateral. Agreed. So then they would conclude that the diagonals are not congruent, and that's where they've made a mistake. Just because this is not true doesn't make this not true. Why? Because the inverse doesn't have to have the same truth value as the conditional statement. So just because we've concluded that the hypothesis is not true does not mean that we can conclude that the conclusion is not true. So we can't say that WY is not congruent to XZ. The only thing we can conclude is no conclusion. And again, it's because the inverse and conditional statements do not have to have the same truth value. Part D. If quadrilateral EFGH exists and EG is bigger than FH, or in other words, the measure of segment EG is not the same as the measure of segment FH. What we're saying is EG and FH are not congruent. This is telling me the negation of the conclusion is true. Well, now that I've negated the conclusion and I'm concluding that that's true, because the contrapositive, not Q, has to have the same truth value as the conditional statement, then I can conclude not P. Must be true. So I can conclude EFGH is not equiangular. Okay. Example 6. State contrapositive, converse, and inverse of each statement. If it is snowing, the game is canceled. Hypothesis, conclusion. Contrapositive, flip them and negate them. If, so this is Roman numeral 1. If the game is not canceled, then it is not snowing. Roman numeral 2. Converse, switch them. If the game is canceled, then it is snowing. Roman numeral 3. Inverse. Inverse is negate hypothesis, negate conclusion, but don't switch. So, if it is not snowing, then it is, then the game, sorry. The game is not canceled. Okay. That's part A. Part B. A square is a rectangle. What are we concluding here? We're concluding that it's a rectangle. Here's my hypothesis. Sorry, one line under the hypothesis. So, Roman numeral 1. Contrapositive. Switch them and negate them. If a polygon is not a rectangle, then it is not a square. Roman numeral 2. Converse. We're just going to switch them without negating. If polygon is a rectangle, then it is a square. Roman numeral 3. Inverse, which negates the hypothesis and negates the conclusion, but doesn't switch anything. If a polygon is not a square, then it is not a rectangle. Part C. Roman numeral 1. Contrapositive. Switch them and negate them. The negation here is going to be a little bit tricky. So you only a little bit. You just got to pay attention to a small piece. If x, so the negation of x is greater than 7. What's the opposite of x is greater than 7? The opposite is x is less than 7. Almost. We're missing one small piece. It's x is less than or equal to 7. That's the one small trick on this one. So if x is less than or equal to 7, then 2x plus 1 is less than or equal to 15. That's our contrapositive. Converse, switch them, but don't negate. If x is greater than 7, then 2x plus 1 is greater than 15. Roman numeral 3. If we're doing inverse this time, so we are not switching, but we are negating. If 2x plus 1 is less than or equal to 15, then x is less than or equal to 7. So that's part C. Part D, last one. If we win the game on Saturday, we win the championship. Roman numeral 1. So, contrapositive. Switch them and negate them. If we do not win the championship, then we do not win the game on Saturday. Roman numeral 2. Converse. Just switch them, don't negate them. If we win championship, then we win the game on Saturday. Roman numeral 3, inverse. Don't switch them, just negate them. If we do not win the game on Saturday, then we do not win the championship. Okay. Example 7. Decide whether each statement about the diagram is true. Explain your answer using the definitions that we've learned. Alright, so part A, we're told the measure of angle AEB is 90 degrees. I'm sorry, we're trying to conclude. Can we conclude that the measure of angle AEB is 90 degrees? Sure. We can conclude this. We can conclude this because AEB, BEC form a linear pair. We're shown that BEC is a right angle, which makes it 90 degrees. If these are a linear pair, by definition of a linear pair, then they have to be supplementary. They have to add up to 180. If this one's 90, this has to be 90 to get it to add up to 180, which makes this a right angle, makes it 90 degrees. True. Okay. Points A, C, and D are collinear. A, C, and D. Collinear. False. They do not line up on the same line. They are not collinear by the definition of collinear. Ray AC and ray CA are opposite rays. Ray AC starts here at point A, goes through point C, and continues in this direction. Ray CA starts at point C, goes through point A, and continues in this direction. Are these opposite rays? No. This is false. Opposite rays share a common endpoint and no other common points at all, and they're collinear. So yes, these are collinear. They have some points that are not in common, but they have a whole bunch of points. Segment AC are all in common. They don't have a common endpoint. So that's false. Okay. Example 8. A biconditional statement is a statement that can be written when the converse and the conditional statements are both true. If they're both true, then we can write this biconditional statement. So we're going to rewrite the definition of complementary angles as a single biconditional statement. Oh, I only have one statement written here. If two angles are complementary, then the sum of the measures is 90 degrees. That's a true statement. It is also true that the converse is true. If the sum of the measures of the angles is 90 degrees, then the two angles are complementary. That's the converse. That's true. Because the conditional and the converse are both true, we can write a single biconditional statement. So instead of writing two statements, we can write one statement that includes the phrase if and only if in the middle. So two angles are complementary if and only if, and that's an abbreviation for if and only if. IFF is an abbreviation. If and only if the sum of the measures of the angles is 90 degrees. Now, of course, because it's a biconditional statement, we can actually write it in either order. It's hard to get this one wrong. The sum of the measures of the angles is 90 degrees if and only if the two angles are complementary. I can write it in either direction. Both are true. All right. Example 9. Rewrite as two if-then statements that are converses of each other. In other words, take this biconditional statement and split it up into the two original statements, the conditional and the converse, that it came from originally. So, if two angles, we use some abbreviations here, are supplementary, then the sum of their measures is 180 degrees. So we'll say that one's the conditional statement. It really doesn't matter which one we say is the conditional. And the converse then is if the sum of the measures of two angles is 180 degrees, then the angles are supplementary. Okay, Alan, Ben, and Cal chose these names on purpose for A, B, and C. Are seated in a row with Alan in the back and Cal in the front with their eyes closed. Diane, D, places a hat on each of their heads from a box that they know contains 3 red hats, 2 blue hats. They open their eyes and look forward. Alan says, I cannot deduce what color hat I'm wearing. Now remember, Alan can't see anybody sitting in front of him. Hearing that, Ben says, I cannot deduce what color hat I'm wearing either. Ben can only see Alan's hat. Cal then says, I know what color I'm wearing. What color is Cal's hat, and how does he know the color? So, to do this, I'm actually going to steal this blank piece of paper here, or this blank side, and I'm going to make a chart. Alan, Ben, Cal. And I'm going to make a chart of all the possible ways that the hats could be placed on their heads. Okay, remembering that there are 3 red hats and 2 blue hats. So, it could be red, red, red. It could be red, red, blue. It could be red, blue, red. It could be red, blue, blue. It could be blue, red, red. It could be blue, red, blue. It could be blue, blue, red. but it can't be blue, 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 because there aren't 3 blue hats. There's only 2 blue hats. Okay? Now, Cal can't see what color hat anybody's wearing, so he definitely doesn't know what color hat he's wearing. Alan can't see. Let me see if I get this right. Alan can't see anything. Alan can't see. They're facing this way. Sorry. Alan can't see anybody's hat, so he doesn't know. He could be wearing red. He could be wearing blue. He doesn't know. Okay? Ben. If Ben sees red, he could be wearing red. If he sees red, could be wearing red. Sees red, could be wearing blue. Sees red, could be wearing blue. If he sees blue, he could be wearing red. Sees blue, he could be wearing red. Sees blue, he could be wearing blue. Well, sorry, I was right the first time. Alan is in the back. Alan sees Ben and Cal. Now, what would be the one situation where Alan would know what color hat he was wearing? Only time that Alan would know what color hats he was wearing is if he saw blue, blue. If he sees blue, blue, he knows there are no more blue hats. And he would know that he would have to be wearing red. But Alan didn't see blue, blue, so he could be wearing red. He could be wearing blue. So Alan didn't see blue, blue, so this situation doesn't exist. Ben knows this. Ben knows that it's not blue, blue. So Alan either saw red, red, or he saw red, blue, or blue, red. Red, 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 blue, or blue, red. Okay? If Ben saw a red hat, he could be wearing red. If he sees a red hat, he could be wearing blue. If he sees a red hat, he could be wearing red. If he sees a red hat, he could be wearing blue. But notice, if Ben sees a blue hat, he's wearing red. If he sees a blue hat, he's wearing red. If Ben saw a blue hat, he would have known he was wearing red. But Ben didn't know what he was wearing, so Ben did not see a blue hat. Cal knows this. What's left? No matter what the situation is, Cal's hat has to be red. So Cal knows he's wearing a red hat. Okay. Now we get into Venn diagrams. Example 11. What conditional statement that write the conditional statement that each Venn diagram illustrates. Okay, so this first Venn diagram, how do Venn diagrams work? Well, everything that is named here is contained in this circle. Everything that's named here is contained in this circle. Well, this circle is completely contained within this particular circle. So everything that's here is also here. So how do we put that into words using Olympians and athletes? All Olympic, capital O, competitors are athletes. Or an if-then form. If a person is an Olympic competitor, then he or she is an athlete. Okay. B. All robins are birds. If something is a robin, then it is a bird. Part C. All whole numbers are integers. And that concludes section 2.1.